but the difference is that, okay, so the difference is that in this one, it used the direct late distribution as the prior, as both for both prior and the posterior. So in this paper, it mentioned two reasons why it used the direct late, but actually I feel it's not that convincing to me. I'd like to, so that two reasons in the paper to choose direct late distribution is, so firstly, for the direct late distribution, actually it has the direct late distribution for the channels in each layer. So the probability for each channel to be pruned were summed to 1, and with this, it can allow us to learn the relative importance of each channel, and such we can rank the channel and choose how much channel to prune. But actually, I feel if we just use the Gaussian distribution for each channel, maybe they are not the relative importance, but I feel it's still kind of the channel importance, and we can rank with that. So I don't really understand why is that. Does the direct late distribution make much difference other than the Gaussian distribution? So for the paper, it claims that this is the first paper to propose to use the direct late distribution for the post-training pruning. That's the contribution. But so do you have any idea why the direct late distribution is better than Gaussian here?
I cannot forget, is the dirichlet distribution is the distribution over the simplex? Yes.
So we can go through the Wikipedia a bit about the direct late distribution.
Is a kind of a softmax distribution. Maybe that's why they want parameterized by Dirichlet.
Yes, I guess the idea is kind of similar to the like transition process. And it will first select the one channel, and if with some property, we'll select the next channel. But if one feature or one channel is important enough, then it will concentrate on that channel and won't jump to the other. But so it has some concentrating effect that will tend to keep those already strong channels, but it will have some property to jump to not jump, but to select some unimportant channels, and then the posterior will give you a kind of distribution according to the importance.
So when you say the concentrate, so you mean that finally it will make the SL, so that's the scaling factor for some channel to be large, for the other to be small. So it can make the network sparse. Did I understand correctly?
Yes. So consider how you construct the distribution. It's like the detailed process maybe Zheng or Shibo, you're more familiar, but it's like it tend to concentrate on some big table, like, or big channel. If first choose those big channel and then has a small probability to choose the unimportant channel.
Yeah, so maybe I can talk a bit about the algorithm again, so it can provide you more information to understand that and think about that question. So
I mean, the algorithm won't
yeah.
tell you why it chooses the digital process or why or the advantage of the digital process. It only tells you how to train the network. But
yeah, because you just mentioned how it will remove how it will decide the important and the unimportant channel and how to remove. So there will be some detail.
Yeah, I mean, you ask why he choose digital other than Gaussian. I just try to explain why digital might be better, or what's the advantage, or what's the meaning or interpretability of the digital process. He choose GT. It has nothing to do with the training process, but the distribution itself.
Yeah. Actually, I would like to say that for this algorithm, there is no actually there is no training on the regular model parameter. So the original weights of the parameter, there is no training on that. There is only training on the importance score. So when so when it applies the KL, the apple as the objective, I mean as the loss. So it will phrase the regular model parameter and then fine tune and then not fine tune and then learn the importance score learn the scaling factor. So in the paper, it said it only requires one epoch to learn that.
So I think it is mainly because you can rank. The ranking is more natural if you use directly prior over the scaling factors, because you can imagine like the importance are only anomalous between 0 and 1. The larger the importance, the larger the probability. Once you got ranking,
yes.
you can just determine according to their importance. If you use Gaussian distribution, how do you rank? The scaling factor can be positive, can be negative.
But in the variational network pruning, so it still use a threshold to decide which layer to prune. I mean, when it used the threshold, so I feel it's kind of like to use the ranking, because it for threshold is also a compression with
yeah, I'm not saying
yeah.
using Gaussian distribution is you cannot do ranking or you cannot do thresholding. I'm saying using dirichlet distribution is a more natural choice.
And in variation case, I think they fully factorize the channel into a single Gaussian distribution, and then they say if its mean is nearly 0 and the variance is very small, which means we believe that the scaling factor is near 0, then discard that channel. Here, it's a joint distribution of teacher.
Yes, that's the difference. So for the variational paper, yes, for each channel they have a single Gaussian distribution, and they decided whether to prune by whether their mean is close to zero, and hope their variance to be small. So in that case, it will be pruned. So yeah.
But
And
it's not hope, it's a criteria that if it means near zero and the variance is also near zero, which means we are confident that the mean is near zero.
Yes.
And also here, I want to confirm with you the detail. So the scaling factor is multiplied again, like in the variational Gaussian case, it's just multiply the channel output, the outputs for one channel. Right?
Yes.
And for the how about for the linear layers, the feed-forward layers, it is multiplied for every output?
Yes, the same. So for the linear layer, if they have an output, so then the scaling factor, the vector of the scaling factor's length is also n.
So it will need to add a lot of like the switch up in the linear layer.
Yes. So the number of the extra parameter, the scaling factor, is the same, is linear to the number of the channel and the number of the linear output. And and so when talking about because I think Panjimo just mentioned mention the order to prune the channel. So actually there is one more detail. In this paper, it started two ways to do the pruning. The first way is called the joint pruning. So it tries to learn all the scaling factor. I mean, in the whole network of different layer, to learn them together. That's a joint learning. Another is that they learn the scaling factor of each layer one by one from the input to the output. So it means that it learns the scaling factor which is close to the input firstly, and then to the next layer until to the last layer. So in the experiment, so they provide when the result has a bracket joint, so it means that it learn all the scaling factor together. And another
time,
yeah.
Jim, I try to confirm it. So what's the joint probability? So the joint probability is still the output to feed to the training data?
Yes. So for the joint, it's not a joint probability. It's a way to learn the scaling factor to be jointly or to learn each.
In any case, they just want to feed the final the neural network's output to the training data, right?
Yes.
But for this layer by layer, once you have obtained the scaling factor for the first layer, so they're gonna fix it, isn't it?
I guess so.
But how do they fix it? Just replace the scaling factor by the mean? of the Dirichlet posterior, or they didn't mention that?
I need to check the paper again. I didn't think that carefully, so maybe I missed some detail. It didn't say so. I think it didn't provide the details. But they released the code. So actually, I think I can
It doesn't matter.
get that from the code.
Yeah, I'm just curious. Okay.
Yeah. So
we can take a look at the experimental results.
Okay. So for me, I feel Dirichlet pruning, not the Dirichlet distribution is as you mentioned, is a very natural way if we want to, if we have a multiple variable to describe the distribution for multiple variables. So it's a natural way to use this distribution. So it seems there is no other special reason for this choice, right?
I mean, their motivation is not that strong. I mean, it's fine. I mean, if you use Dirichlet distribution, if you
I agree.
Yeah, but it's not. I mean, you can also do like, let me just apply a binary variable, or you multiply a binary variable with each channel as a scaling factor, right? They're just independent. You just ask them a posterior distribution for each binary variable. This is another switch.
Yes. So in the paper, it also mentioned some other distribution. So I think last time you talk about the horseshoe, right? So actually, in this paper, it also mentioned that it seems that there are some paper has already worked that, but for those methods that are used for pruning during the training. So I think the contribution this paper claimed is that this is the first paper used directly the pruning for post-training pruning. Yeah, for me, I think it's not so. The motivation is not so strong.
Yeah, I mean, if you use binary variable, independent binary variable for each scaling factor, you can even use concrete distribution, the relaxation of that binary variable. I think it will be even easier for the posterior inference. I mean, from technical part, I don't see any solid contribution here.
Yeah.
If you think there are some downstream applications to use the importance score to select the most important channel, and this might make some sense.
Okay. Yeah. So
because
you're right.
Yeah, because Dirichlet distribution is always used as a prior distribution for the for hyperparameters of a categorical distribution. So if you treat the importance as the parameter of a categorical distribution, that makes some sense.
And
Yeah.
I have a
Okay.
question about, so if we can select channel or select neuron using this method, Dirichlet or Gaussian, so could we use this method to like select a feature? For example, we just apply to the first, to the, like we were doing a linear regression problem and we apply the technique to the first layer. Could we select like useful feature from using this method?
How do you define the feature? So you mean the output of each feature map, each element. So assume the output is B by C by H by W. So do you mean each element in that tensor, or
No, a feature vector, a simple feature vector. If we apply we append a switch to each of the feature vector. We have like 10 features, and I use 10. I add 10 switches to after the feature vector and do a linear regression. Could we select useful feature out of this method?
you mean the feature is the input?
Yeah.
Oh, okay. So it sounds like the some. So you know that in the visualization technique, so they try to learn some salience map of the input. So it can help to visualize which part of the image is important. I mean, for if the input is the image.
No,
So
as just a feature vector, I didn't see why, if we can select important channel or neuron, why we couldn't select important or useful feature. It seems to me.
I feel there would be problem. The reason is that the reason is that I think in the neural network, so after for well-trained model, so the one channel can be more important than another channel for all the input, but for the input itself, for the feature of different position, you cannot say that the feature in one position is always more important than another position. So I thought maybe it's not a good way.
What do you mean other position?
So what I'm trying to say is that I mean for one input, you can learn which feature. Assume we have the index of the element in the feature. So for index 1, index 2 until index n. So assume it for the input 1, index 1 is more important than index 2. But for the second input, maybe index 2 is more important than index 1. So I mean, it's hard to I think the which input feature is more important dependent on the input. There is no fixed position that the feature would be more important than the others.
But that's the idea of feature selection, right? We want to select some features because like we have 100 features, then we only want to keep 10 of them. You have to keep 10 of them. So what's the highest probability that we can select the top 10 features? Maybe it seems like you run Dirichlet and rank by the top 10, let's say. a doable solution.
I get your point. I still feel there is some different from this case. I think for the channel pruning, which channel to prune can be fixed for all the input. So I mean,
you can do that, Zhimeng, but you really have to do this during the train. I mean, you should train while pruning the features.
yes.
Yeah. Yes. So like it seems like we can train and put aside some distribution over the features, and then we select we can discard some of them and then train again and discard.
Yeah,
some of them.
this is important for some medical applications, like what Zheng has done. Like you have we have thousands of features, 2,000 of features. We don't want to incorporate all of them into the neural network. Then you might consider such methods to prune the features during the training.
I see. I mean, this all this paper I do like channel pruning, but I didn't see why this idea couldn't be applied to feature selection. And during a review, interview or something, they say, how do you select the features? And maybe I only ask L1, L2, but maybe there's a bunch of like distribution-based feature selection measure.
Yes, I would like to say yes. Maybe you can try this method to select the feature. So, but the additional task you may need to do is that you need to decide where. I mean.
Okay.
We
can continue.
Which feature? I mean, where is the feature to prune? So it will dependent on the input. So my feeling is that actually for the input, if for a feature vector, if you change the order of each feature, I guess the output should be the same. If just for the regression. So
then what's the problem?
What I'm trying to what I'm trying to say is that if you have a set of feature, so
I think Zhimeng's problem can be like compared with node, can be treated as a node pruning here, because he want to just do the feature selection. You can treat it as a node pruning. I think the method can also be applied to the node pruning problem.
Here, I mean, this paper is also node pruning because you say it also applied to the like linear layer. Then
yeah, a channel can also be treated as a big node.
A big node, yeah.
Yes, but for each channel, actually it corresponds to one filter, right? For one filter, it has the semantic meaning. It will extract a certain feature in certain feature. So I mean, its semantic meaning is kind of fixed for a well-trained model. So that's why when you have different input, you can decide. You can. I mean, the importance of one channel can be the same for different input. So, but for the input feature itself, I mean, the node will be the node somehow is the location of each feature. So the semantic meaning can be different for each location. Then I feel how to decide the important score is the or
maybe you limit yourself only to image problem, like we directly use an image to do the regression from the raw image to the result. And now we are talking about like a general machine learning problem. We just gave you a feature vector. It's only already feature. It's not like the pixels of the image or like a RGB. So you might think you use RGB is not, we won't be able to select which pixel to use. But if you think in terms of a general feature vector, then for a instance, it will have a set of semantic feature, like the height, the width, or the color, or the some characteristic of one training instance. Then they have very specific meaning, or maybe some features are important or related to your task, but some are not.
Oh, okay, I see. So I think the formulation for that problem is that the p scaling factor given a single feature, right? So at first I thought it's the p the single feature given a position, given a position in one feature. Okay. Yeah, then I think of course you can try the direct late.
Yeah, let's move on.
Okay, so okay, and in this paper, so the parameterization and trick, there are two trick. It's different from the variational network pruning. So the first is the implicit gradient computation. It tries to compute the gradient of the inverse CDF of the gamma distribution. Another is that it use the mean of the directly random variable.
Where is the gamma distribution?
The gamma distribution. So when you look at the apple, so it has so when you look at the original directly pruning, actually there is a, it used the beta function as to normalize the term, and for the beta function it has a gamma distribution inside, and so when you calculate this apple, there will be the gamma distribution.
Where is the expectation term? I didn't see the expectation term.
So I think that's the
KL should be expression over something. What's the expression?
I think that's just how you conduct reparameterization trick to the Dirichlet distribution. They just use the inverse accumulative of accumulant distribution function to do the reparameterization.
So let's see.
Xing, I think the gamma distribution only appears in the reparameterization, right? How they generate a random variable from a Dirichlet distribution.
Yes, it is used the reparametrization. So
Oh,
actually
okay.
here, I think the capital beta, actually that represents the gamma function.
Oh, the KR of
Oh, the
two
side.
Dirichlet has.
Oh, it's a
The
gamma
KR
function. Okay.
I see. So the KR is closed form, and they need to sample from its closed form, so they use the CDF.
Here I didn't for this one I didn't get the formulation by myself, so I didn't know much detail about it.
Okay, for the KL divergence, you don't need to worry about because they have the closed form, and the gradient of the gamma is there. You don't need to worry about that. I think the major issue is how do you, in the likelihood, you have an expectation of the likelihood, so I have to reparameterize the posterior of the Dirichlet posterior, and to get a parameterized sample.
Yeah, so so in the two yeah, I think for the implicit gradient computation, they use a sample. So in the paper, they mentioned that they use different number of sample to compute the gradient of the inverse CDF, and for the second method,
Why do they want the inverse CDF, inverse gamma CDF?
I don't know. So
Oh, that's a way to reduce the variance.
Yeah, the paper said you can sample from sample Dirichlet from sample gamma. Just slightly below. In the section.
in which paper? In
just this one.
Oh,
just
okay.
scroll down slightly below. Yeah, there.
For the gamma distribution?
No, the beta and Dirichlet.
Oh, okay. Oh, okay. So samples can be obtained from gamma directly. Okay.
The problem is how do you get? They said that how do you conduct the implicit gradient computation? The motivation is to reduce the variance.
You can just scroll up a little bit, and here I think here is how they conduct the implicit reparameterization.
So what's the S inverse here?
So when they use this implicit reprogrammation in calculate the gradient, they need to manually calculate gradient and then apply to update parameter. Right. It seems like you won't be able to use the directly use the gradient.
Oh, I don't know. So I think for this one, for this I need to. I mean, I need to follow that to get to figure out each step. Otherwise, it's I didn't understand it so well.
Okay, I guess this is just a computational trick. Yeah, we just take a look at the experiment's results because it's not it's unclear. It's less likely we're gonna reuse their technique. Let us just look at experimental results.
Okay, and actually, I still have one question here. So after, after the for the direct later distribution, actually they were learn the alpha. So when they learn the alpha, how did they get the important score? So do they use some sampling or just use the similar way as the parametrization trick? I mean, how did they get the scaling factor? I didn't get that.
I think they just get the mean. As long as you got alpha, you can calculate the posterior mean of those scaling factors and the runtime.
Oh, okay. Just like the Gaussian use the mean.
Yeah, I think so.
Okay.
You can see how they define the scaling vector through the distribution.
What do you mean how to define the scaling factor?
What's the definition of the scaling factor?
You mean in mathematically or just?
So it's S, right? So the division sum of one.
So I think it defines the posterior over the scaling factor. I guess they
sample it from the posterior. So maybe if it's the mean, or you could sample multiple times and see the and calculate the practical mean. So literally you can directly, if you have the closed form posterior, then you know the posterior mean. You can use the posterior mean as the importance and do the problem.
Okay, I see. So it's from the mean of the posterior. When we get the fact, when we know the variable in the direct later distribution. Okay. All right. So so here this is the experiment result. For the last column, actually that's the result of the variational convolution network pruning, and there are two metrics to evaluate the pruning. The first is the error, that's the test error. So the larger is worse, and the second is the float. That's the float. That's the float operation, number of the float operation. So the less means that the network is faster, and so the smaller the number is better. So for the direct late method, it has the lowest flops, and the number of the number of the parameter is also relative. I think it's the second lowest, and but the error is comparable to some larger network.
Okay, what's the flops? The flops is for the pruning or for the
pruning. So there are different ways to.
You mean they use a much smaller cost to prune the network?
No, not for pruning. It's after pruning. So for the it's actually is that so.
I think they just say
for network, the number of the operation is different, can be different. Even the model size is the same.
So the new model, the smaller model, uses smaller cost to make predictions.
Yes, to use less computation cost. This is for the computation cost. And for the parameter, that's for the memory cost.
I'm curious to know why the BC GHS they use 4 times the number of flops with the same number of parameters, or even smaller number of parameters.
Yes, that's what I'd like to explain. So that's because it's decided whether you prune the linear layer, prune more on the linear layer, or you prune more on the convolution layer. Because for the convolution, you have the convolution. The difference between convolution and linear layer is that for convolution, the filter size is smaller. It means that the parameter size is smaller, because in general you just has the C1 by C2 by somehow like the 3 by 3.
Mm-hmm.
So the filter size is small, but you need to slide that filter through the whole image. So it means that you need to repeat that operation for many times. So the overall computation is much more heavier than the linear layer. So when do the pruning, if you prune more convolution layer, it will reduce more flops. And if you prune more linear layer, it will reduce more parameter.
So in the BCGHS, they mostly prune the linear layer.
Yes, it not mean that it prune more linear layer than direct late method.
But it also tries to prune the convolution layers.
Yes, sure.
Okay.
I have a question about this float. So float in the convention meaning, it means floating point operations per second. But
not per second. S is the operation.
Operations.
Plural.
Yeah.
Okay.
Yes.
It just means floating point operation.
Yeah, it's not a mean second.
Of the single model.
Yes.
Okay, I see.
Yeah. So because for this one, this is the WHG 16 on CIFAR 10. So because it compare with the variational convolution network, so I put it first, and it also do the evaluation on the other network.
Where's the variational pruning method? VP?
Yeah. That's the paper we talk. The last paper that's the paper I presented last week.
The variational pruning only prunes convolution layers, right?
Yes.
But it's much fun. It's much better. Looks like.
Yes, but the model is larger, right? The model is 5 times than the direct rate.
Why don't they just prune more with VP and C, then compare the performance?
Maybe because most of parameters will is on the linear layer. There's not much to prune in the filter because filter size is really small.
But VP should also prune a lot of convolution layers as well, right? VP doesn't prune linear layers.
Yeah.
Yes.
So
Yeah.
that's why
So
that's why last time I asked why they don't try to use VP to prune the linear layer, and the answer is no one do that. No one did that. So I'm not satisfied with the answer actually.
Or in other hand, like you can like fix the linear layers. You just use dirichlet to prune the convolution layers and compare the performance and see what happens.
yeah, and another difference is that for the VP actually is pruning during the training.
Oh, okay.
Yeah, so this is a post training pruning, and then do the retrain.
Yeah, but I'm still a little. I guess they just copy the numbers of the papers, right? They don't want to run their.
I think so. They mentioned that they just get
Yeah,
the
if they
number from
really want to
papers.
do a fair comparison, they should just preempt their linear layer pruning. They can use their dirichlet to only prune convolution layers and see what's the difference.
Yes, but for VP they didn't release code.
I mean, for dirichlet itself, for dirichlet pruning itself, it is very easy for them to
Just prune the
just
convolution.
prune the convolution layers.
Yeah, sure.
Yeah, let's see. Let's look at other results.
Okay. So so I mean
this is for the LearnNet.
Yes. Yeah. The LearnNet should this for LearnNet this should be on MNIST. I need to check is on MNIST or MNIST fashion.
The NET could achieve such low accuracy on MNIST or of Cypher. I mean,
this is I think this is not on Cypher.
yeah, this should be MNIST. Cypher they won't be able to achieve such high accuracy.
Yeah, this is I need to check it because they have two data set, MNIST and fashion MNIST. So for table 1.
It doesn't matter.
Yeah. Okay.
Doesn't matter.
All right. So so for the other result, it's kind of they can always get the smallest model and get the comparable accuracy.
So they don't put the VP results just because the VP doesn't give the code, so they cannot conduct.
I think for this one they have a different architecture to test.
So VP doesn't apply.
I think so.
Why? As long as you have a versional As long as you have convolution layers, VP can be applied, right?
Yeah, sure. So because the VP didn't release code and they just copy numbers from the paper, and also they copy numbers from the other paper, I feel their strategy is that just compare on one network, which overlap with the other method. So for the WG16, they can compare with VP, and for the LearnNet 5, they can compare with the other method.
Okay.
Yeah.
So what does directly 150 mean?
Yeah. So that is as mentioned before. So they use two parametrization trick. The first one, when they use the implicit gradient computation, they need to use some sample. So for 115, it means that they use 150 samples for this one.
Oh, really?
Sample for what?
Sample. I guess it's sample. I mean, it's trying to sample to compute the implicit gradient computation. So.
No, I think it's just the sample the posterior distribution. So you don't. I mean, one posterior sample, one reparameterized sample is not sufficient. They use 150.
Okay. So
they don't need to. Yeah, they don't need to worry about implicit gradient computation. These are all implemented in PyTorch.
Oh, okay. So you mean that with one they have multiple samples, and for each sample they get the scaling factor.
Yeah, and then plug in, they get a more accurate estimation of the.
I see.
Estimation of log likelihood. Yeah.
Okay. Yeah, I see.
So in calculating one gradient, they need 150 samples. Is that right?
Yes.
That sounds crazy.
Yeah.
Is that too expensive?
It's on euro. It's on euro.
Oh,
like you
okay.
have 150. You generate 150 posterior samples for the stochastic gradient descent. Maybe one sample is one reparameterized sample is not sufficient. But I don't know why they generate 150.
Yeah, actually they have some comparison. So on this different data set, so there is a IS that's the important score. So there it uses 150, 300, and 500 different samples, and the mean is the second reparametrization trick. So in most case, the mean performs better than the others.
What does it mean for number of architectures?
Okay, yeah. Actually, this is also related to what Jen just Jen's case. So Jen mentioned that maybe this directly the distribution play an important role to the downstream application. So for this one, it kind of try to say its function. Say that for this method, it's kind of like kind of funct as search over the sub architecture. So actually, I didn't really understand what they are doing. So what they do is that they design a pool of sub architecture with a compression rate range from 20 to 60. So it means that the sub architecture are predefined, and then they run the different methods. For all of those methods, they can rank the important score, and then with the importance score, they were kind of found the network be consistent with the target sub architecture. So it will count how many times times one method can achieve the target sub architecture. I mean, I feel it's a little weird to me. I didn't know how did they design the sub architecture, and secondly, how to make sure that they can get the target sub architecture. So for some sub architecture, they can test that sub architecture can perform better than the others, and then they will say how many times one method can get the sub architecture which perform best. I mean, this process is a little confusing for me.
But what does the L1 norm, M2 norm, IS mean?
IS is the important score. Is this paper, and everyone norm, I think it's kind of like a magnitude based pruning. But
Okay.
for L2 norm, I don't know. So
Maybe it's a Gaussian.
So the numbers, the higher the better, or the lower
the higher is better.
then
So-
one L1 and L2 norm is much better than IS most of the case, except IS mean.
Yeah, that's it.
What? So you see the x-axis, you have IS 150, 300, and 500. And those simple methods are much better than this proposed one.
Yes.
And then the mean is significantly higher. What caused this big differences?
Yeah, I don't know. I mean,
So what does the 500 mean here?
500 is what we discussed, the number of the samples, the number of the sampling from the posterior, and
The mean?
the mean is the method. We didn't the second method we didn't use need to use the
analytical.
this one.
Okay.
Oh,
This is a delta method. Well, you can take a look. It's a delta method. So they don't do, that means they don't do reparameterization. Just shove the posterior parameters in. They just replace SL by the expectation of SL.
Yes.
what? And that can mean of-
They don't include the, yeah, this is the, but they don't include the second term, the gradient term.
No, I mean, this is the bottom line is actually the expectation of a log likelihood, right?
Right.
And you can do this by do the reparameterized to sample SL. You get a reparameterized sample of SL, you plug in this log likelihood. That's our unbiased estimate of the expectation, right?
Yeah.
Another way is that, okay, you can use the delta method we have used before. The delta method means that you just, if you want to calculate expectation of a function, you just replace the parameter in a function by the mean of that parameter. In this way, you even do not need any reparameterization.
Yes. Yeah, right.
That means their analytical mean method is even much better than the reparameterization trick.
So this is the expectation of the posterior over the likelihood, just sample phi from the posterior and then just average. Yeah, okay.
It's not sample like SL. SL is parameterized by SL. The posterior distribution of SL is parameterized by phi L. So you just replace SL by the expectation of SL, which is just the phi L I phi L J divide normalized.
What's this method for? It seems that I have never heard it.
It's called delta method. It's a like Shibua, both Shibua and Shikai has used them before. Like something, if you want to calculate expectation of theta, right? According to some distribution of theta. If you use Taylor expansion, it is easy to show that this is this can be approximated by just replace theta by the expectation of theta. This is called delta method. So this guy is actually expectation of log likelihood, right?
Yeah, yeah.
And then if you want to compute the expectation, well, one way is that, okay, I'm gonna generate a sample of SL and then shove in. That's the reparameterization trick. The other way is that, okay, I'm gonna just move the expectation inside the log likelihood. Okay. This guy is actually this.
Then you calculate the gradient according to this approximated form.
Yeah,
the log.
you calculate gradient because now the gradient is only with respect to phi. You don't need to do any reparameterization trick. It's very, it's a very simple but quite useful trick.
Then the requirement is that you can calculate the expression of theta over whatever is required.
Yeah, as long as you define the posterior distribution of theta, right? So you know the parameters. You should be able to compute expectation of theta according to Q of theta.
Is that similar to the conditional expression proposition?
Yeah, yeah. That's the trick we have used in CEP.
I see. Okay, so this method is much better here in this use case.
Yeah, this method looks like it's better than this so-called implicit gradient computation. This implicit gradient computation essentially is their reparameterization trick.
But they use 150 or 500 samples from the posterior. I thought it should be highly accurate.
Yeah, that's something I feel surprised as well.
And especially so, I think it seems that the 150 samples performed better than the larger number of samples in the first two on the LearnNet.
So what's the result in the compression? Can you go back to the first? Yeah. Okay. Mean and 150. Here the sampling method is basically the same as the analytical one. The mean method. The mean is still a little bit better. And then what's the joint?
The joint means that when they try to calculate all the or the posterior parameter.
Yeah, that's weird. I mean, if you apply directly with mean, you can also do it layer by layer or jointly. Why do
Yes.
they list the directly joint separately? And also directly hours, what does it refer to?
Maybe they just pick whichever is the best.
Yeah, so actually, that's another reason I didn't like this paper much. I think they miss some details.
Okay, that's fine. Let's move on. Let us move on.
And finally, they also provide some visualization about so they use some visualization method to visualize the high dimension feature into the RGB image. So they are provided the top 3 important feature and the least important features. So there are some arrow, the green arrow. So the red one means that the red one means that they have more activation. So I understand that the activation is that for that area they have larger values after multiply with the scaling factor. So actually, I didn't understand why. So it says that for the top 3 important features, they try to learn the outline of the figures, the outline of the numbers, digit numbers. So for the least important features, they didn't do that. But I don't know. I feel the least important features also make sense to me.
Okay. Did they
Yeah.
provide any explanation?
What do you mean? Any explanation?
I mean, why they are least important? Why they are most important?
Yeah, they said for the most important, they have a strong activation in only a few class distinguished place.
That's where the green arrow points.
Yes. And I think for the least important feature, actually they have the
So they say feature, they mean channel. So that's the top 3 important channel. So you can see a whole image as the activation map or the response of a channel. So they say the top 3 channel is important because on this channel, and they have some specific they say class distinguished features. They point using the green arrow. So of all the top 3 features, they will they will focus on 3 different area or angle, so they call this complementary. But the least important feature, as you see the activation map, like the activation spread across the image, and you won't be able to classify a object using this activation map. It's not like an important feature.
Yeah, they mentioned the overlapping. So for different feature map, for the important one, they didn't overlap each other. But for the least important feature, they can overlap with the important ones. I think for the overlap, it kind of means redundant.
Yeah, an important feature means that if you have a 0, then you should have this part, like this round part and the middle part. But for the less important feature map, it kind of spreads out across all the images area. There are many digits could have such activation map. Right. Yeah, it makes sense to me. So it's like a feature selection process.
Okay.
Yeah, let's move on.
Yeah, so in the next, I would like to talk about introduce the knowledge distillation. So for knowledge distillation, I would like to talk about the first paper, distilling knowledge in a nature network. That's a very, very old paper. So the definition of the knowledge distillation is that it tries to use a small network, tries to train a small network to mimic a pre-trained larger network or an ensemble of models. So the motivation is because in general we can use the ensemble models or use a larger models to get better performance during the training, but that the large model would be too resource consuming for inference. So the problem would be, can we develop some method to compress models just for inference? So it means that for knowledge distillation, in fact, we can have a different model for training and for inference, but we can distill the knowledge during the training into the model for inference. This is the motivation. The idea is that actually another work earlier than the distillation paper is that they propose that they try to transfer knowledge from a larger pre-trained model to a smaller network by training the smaller network to mimic the large network's output, the exact output. But that can be a problem, because for a larger network, the accuracy is always high. So the larger network's model's output is close to the ground truth level. so the performance is not so good in this method. And then there is a Hinton's paper. It called this method as distillation. And the key method they proposed is that they modify the softmax with the temperature. So here this is the QI. The QI is the new probability they proposed, and the ZI is the logit of our class in the output of the model, and the ZJ is for the other classes, and the T is the temperature. And when T is equal to 1, it called the hard output. It will become the same as the paper in 2006. So it means that it will try to.
I'm still unclear about what's the difference between the 2006 work and 2014 work.
So for only when T is equal to 1, it's the first paper, and when T is not equal to 1, it's the second one.
But the training procedure isn't the same. The training and inference. I mean, the idea.
Yes, the idea is the same. Only so actually, so for this paper. It's a workshop paper, but the citation is about 220,000 now.
Yeah, I know that.
Yeah, so I think it's a small idea. So just the difference is the temperature is different.
Okay, but what about citation of the 2006 paper?
I didn't check it. So we can look at an example about the difference between the hard and the soft target. So in the first line, that's the original hard target. So that's the one hot vector. So I think that's the ground truth. And the second line is the output of the geometry ensemble. So that's when you talk about the geometry ensemble, actually that comes from, this example comes from the ensemble of models. So actually they propose different large model, and then they do the geometry ensemble on their output. So we can say that the difference between the first most purple prediction, dog and cat, is large. One is 0.9, one is 0.1. And if we use the soft, softmax, so the difference would become smaller.
So where does the ensemble come from?
Ensemble come from actually it's because in this paper, in the distilling knowledge paper, actually they try to, the problem they try to solve is that if we want a high accuracy, one way is that we train multiple models and then use the ensemble of the models to do the inference. So when we use multiple, we need to, one way is that we use the average of their output.
Mm-hmm.
And another is to use the geometry mean. Geometry mean is mean that they multiply the output.
Okay.
Yeah.
I understand. What is geometry?
Yeah. So it can make the it means that only all the I think it's more strict than the average. So only when all the model have high probability for certain class, the result would be larger, and it
But
can.
here the third line, the soften output. So do they all choose like big T?
Yes, I remember. I remember.
Instead of large T, like T equals to 2 or 3, they train
Yeah,
it and then do
yeah.
the
When
average.
T is greater than greater than 1, it will make the difference become smaller.
Which difference?
I can actually I can show you some examples. So yeah, I also didn't understand well how it performs, so I searched some example for that. Oh, okay. Yeah. So maybe we can. I think they provide the code and they provide some example. Yeah. So for this one, actually, this is the number is 5, but this number looks like a 3 somehow. That looks like 3. So if without the soften, the probability between 5 and 3 are large, and with the soften, the probability between the 3 and 5 are small. So it can reflect the similarity of the similarity of the input to certain class. So and for this it's 2, and it somehow can be looks like some other numbers. So it says that it looks like most with 7. So it can make the difference of the output become smaller.
So I mean the smaller the difference, the better.
Yes, for this knowledge distillation, not for prediction.
Or what do you mean? If you set the temperature to infinity, then everything will be uniform distribution. Then what's the meaning of it?
Okay, so I think the tuition here is that. So for this one, this is a character 2, and somehow it looks similar like 7, the up part. But if we just use 1 hot to represent this number, we cannot tell whether it's a 2 looks like 7, or whether it's a 2 looks like 3. But with the prediction from a large model, it can tell that.
Is the prediction of a softened model, right?
Yes.
Okay.
Yeah. So that Hinton called that's the dark knowledge.
So he said instead of producing a nearly 1 hot encoding, we should produce a more more normalized or spread out distribution over the label, so that our student model could learn from distribution instead of a 1 hot encoding. Is the meaning?
Yeah, it can learn more than one hot representation, because it can show the similarity between different class.
So the
How does this dark knowledge lead to distillation? Or
They called the dark knowledge. They try to mimic the dark knowledge. So that's the knowledge distillation.
maybe you should continue. Yeah, like we understand this could somehow change a nearly one-hot to a non-so one-hot distribution, but how does this relate to the distillation?
Okay, so you want to know how did they learn this? So right. Sorry. What do you mean?
I mean, you can.
Yeah, we just want to know how this lead to distillation, because you said distillation is to learn a much smaller network, mimic the output of.
Yeah. I would like to talk that in next slides. So firstly, introduce the loss. So here, in this example, both the teacher network and the student network are trained on the same training data. So the teacher network is pre-trained, so it would be fixed and will not change. And for the student network, it is to be trained. So the loss is that from given one input, we can get the solved labels from the prediction of the teacher, and for the student network, we can also get the prediction. So it will calculate the difference between the here is not the calculate the difference. Here is that it use the solved labels as the target of the prediction. But there are two loss. One is use the soft label as the loss. Another is use the hard label as another loss. Maybe I should show you here. Yeah. So there are two components of the loss. The H here means the cross entropy. So for the first one, that's it has the loss. It has the loss compared with the ground truth Y. So it's the original loss. And the second one is the loss between the soft label of the teacher and the soft label of the student, and they use the same temperature here.
So temperature tau here is usually bigger than 1.
Yes.
Oh, I see.
Yes. Yeah. So there are two components, and there is for alpha and beta. They have some. They have some empirical number for this, and so if the beta is equal to 0, it's the same as the regular training.
So the idea is for the student network, first it should learn to predict the correct label, and then it should follow, or it should try to, or it could be regularized by the teacher network that the predicted distribution for one label should be basically the same, or they will try to minimize the KL divergence of the predicted distribution.
No, for this method, they didn't minimize the KL divergence. There is other paper try to do that. For this paper, they just use the soft label of the teacher as the target.
What's the edge here? What's the edge here?
Cross entropy.
And it's KL divergence. if you minimize cross entropy of two distribution, it's essentially minimize scale divergence.
Okay. Yeah, that's then this method, okay, that's great. Then this method can be, I mean, this method and the other method can be in the same framework now.
So tau is how do they choose tau?
Hyperparameter.
Is also tuned along with alpha and beta.
Yes. And
Okay,
Then why not they just integral with tau?
Yeah, I just thought like, how about like choose many tau, like 0 tau?
Yeah, they are trying like you put some integral here, right? And from
okay.
0, from 1 to infinity or whatever.
Or just
So-
choose several, like low temperature, high medium temperature, or high temperature. Then you should try to produce it same distribution or like several temperature range.
So I think in the paper they didn't mention this. They mentioned some other tricks with regard to the ensemble. So yeah.
So in the training, you can choose whatever the architecture you want, but just the
Yes.
loss will be the like regularization or enforcement.
So you mean that are you going to change the student network during training or not?
So I mean, in the whole process, the only thing the teacher model provide is the like the logic distribution. That's it, and any other thing any other thing the
No.
student decide, like the design of the network architecture has nothing to do with
No. So that it only provides the soft labor from. I mean, the teacher network only provides the soft labor. So I mean, that's the advantage, but maybe also a disadvantage of the distillation. So for the student, it has too much freedom to choose the architecture, its own architecture. So yeah.
This is the very early paper, so not now. Like I mean, today, when they say knowledge distribution, are they still following this framework? Like teacher model only provide a soft label.
No, not. So yeah, so there are. Okay, so we can continue, and I will mention that. So this is the current this is the old architecture. So for the old architecture, the teacher model and the student model, they didn't have any interaction between each other. So the teacher model only provides a soft label, and it provides a distillation loss to the student network. But yeah, this is just one experiment. But the new trend in the distillation is that firstly it provides a multiple teacher. So and one student, and also introduce a teaching assistant. So a teaching assistant is somehow like that. There is one teacher network distill knowledge to a TA network, and then the TA network distill knowledge to the student network. I saw one triple AI paper last year to do that. So
what's the benefit of doing this?
Like a multi-stage.
Yes, multi-stage. So I think this can be benefit for the transfer learning. So if one TA network is try try to distill one kind of knowledge, and another try to is kind of disentangle the knowledge from the teacher network. But I don't like such architecture. So for this one, another I haven't put is that beside currently for some architecture for the distillation, besides the output from the last layer, they also provide to mimic the intermediate features of the teacher network. There can be different way to do that.
Okay.
And so for me, I feel the knowledge distillation for me is kind of a concept. I mean, it's not a mathematically it's not a math formulation method. It's just a concept. People can use the knowledge distillation to whatever people want to do. If there are a student network and a teacher network. So another paper I try to cover is based in dark knowledge. For this one, it tries to distill a Monte Carlo approximation to the posterior predictive density into a single network. So in my understanding, it tries to distill the Bayesian neural network, the prediction into a regular convolution network. For here, it used the KL divergency as the objective function, and it proposed some method to actually I spent some time on that method, but I didn't understand well, so I didn't finish the slides on that. I mean for this one, the knowledge distillation is to distill the Monte Carlo approximation. So it tries to distill the posterior prediction into a CNN.
So you mean the student network is also a CNN?
Yeah, the student is CNN.
But the teacher network is an aperture network.
The teacher network is the Monte Carlo ensemble.
Okay, but when they train that, they still use the original training set.
No, because I think that's the difficult. No, not exactly. So they propose some. I think maybe you are very you get maybe very familiar with this one. If I show you the algorithm.
So in general knowledge distillation task, we don't use the original network to train the student network. The original data set to train the student network.
Sorry. Yeah, could you say that again?
So in the general task of distillation, we don't use the original data set that we train for the teacher network
No,
to train.
they still use the same data, but in some I'm trying to say for this one they still try to train on the same task, but for the knowledge distillation itself, there are also other papers. The train and the test are on different tasks. So that's used in the transfer learning.
Okay, so in a general distribution task setting, we train and test the student and teacher network use the same data set.
I mean, I can say in the original.
Or the same data set.
Yes, in the original distillation, they are trained on the same data set, but when it develop, actually, it can be different. The training, they can be two different tasks.
So that's the like a transfer learning setting.
Yes. Now the distillation has already been used for transfer learning.
Okay.
Yeah. So.
Okay, here we go.
Yeah. So. Actually, so here, this is the objective function. So they have the K divergency. So for the W means the weight of the student network, and this is the first term is the teacher network. So that's I think that's a Bayesian neural network. The formulation for the Bayesian neural network. So for this, this is a loss. And when they try to solve this objective, they need to compute a Monte Carlo approximation. And for to calculate the Monte Carlo approximation, this is what they use, the SGLD. It's a different. It's different than SGD. So maybe you are familiar with this one. Did you say this one before, or
What?
do you use this one? It's a different. It's a different. Yeah.
What's the full name of it?
Full name.
Stochastic gradient Langevin.
Langevin. Okay. Yeah.
Yeah.
Guess it's
Who has
Langevin.
presented this before?
No?
Yeah. This is what they used, and they propose. Yeah. So actually, I didn't figure out how did they do this algorithm.
So they cannot jointly train the student and the teacher and student. Like alternatively train, update teacher and then update student.
In this one. In this paper. So
why they need to train the teacher network alongside with the student? I thought the teacher network is not given.
I think it's related because they proposed the SGD as a replacement of SGD, right?
Oh, okay. So they want to posterior samples of.
Yeah.
And what does D prime here mean?
D prime.
Yeah, the last line in the table, count with 1.
Prime.
Oh, D prime. Oh yeah. So actually that's the I think they try to distinguish the data in training and the data in the data in the student network and the data in the teacher network.
Oh, okay. The D prime is to train student network only.
Yes. So yeah, I felt maybe they can be the same.
Yeah, they can be the same.
Yeah, but they try to distinguish them. Also, we can say that from the formulation here.
So what's the idea of it? Like what does it try to like minimize?
They try to minimize the KL divergence between the prediction of the Bayesian neural network and the CNN network.
So their prediction has a distribution. Okay.
Yes. Actually, I think the distribution of the Bayesian. I mean the Bayesian prediction have the distribution for. Yeah.
I
So
think the bracket, the bracket inside the bracket of 1, it is the cross entropy, isn't it?
Cross entropy.
Yeah, there's a expectation of the log of prediction of the student network under P of Y given X and theta. Is it cross entropy? If you're doing classification, it just tells you the output distribution by the teacher network, and the S, Y given X and W is the output distribution for the teachers, for students prediction.
So in my understanding for cross entropy, I think it's for example for YI it have multiple choice.
Yeah.
And here it seems that it's given theta. Can this review?
Yeah, like you can imagine this is a category, right? Like 1, 2, 3. So you have a softmax output given theta. And you also have a softmax output given W for your teacher network. So this is just a
I think it's just the cross entropy because
the cross entropy.
The KL between P and Q is the cross entropy between P and Q, and the entropy of P itself. P itself here is a constant, so ignoring it, then it's the entropy of these two distributions. That's why in Hinton's paper they say he said it minimized cross entropy between that two terms. I said it essentially minimizing the cross entropy.
Okay.
Here, if we are doing like a classification and as Y given X and W is a sigmoid, then it will be the same as the Hinton model.
But I still feel there is some difference. Yeah. So for the expectation itself, it looks like a cross entropy, but here it needs to do the integral over
Yeah, you need to
theta.
take expectation over theta again, because this theta is generated from the teacher.
Yes.
That's why in their algorithm 1, they continuously generate instance of theta.
Oh, okay. Okay, but why not the just finish the training of the teacher? They can still
No, they cannot.
can.
The SGLD has to, SGLD just generate the posterior sum of theta during the SGD-like procedure. So if finish training, you cannot generate samples.
Okay.
Like you can consider, like, if you replace the SGD, like why do you move to algorithm 1? I can show that. Okay, if you replace this procedure, right, you just remove it, right? You use any other posterior distribution, like you got variational inference about theta given the training data dn. Okay, this theta given dn. Or you can just remove this line and keep the whole for loop, where each time you're gonna sample theta from the posterior distribution, and then you sample a mini batch of the student data and do this update.
Hi, Shandian, I didn't see your annotation from my side.
Oh, that's bad. Let me. So can I say it again?
Yeah.
No.
I wrote P of theta given D.
No.
No.
You cannot see?
Cannot.
Okay. I'll just speak. So you actually can remove the lines about the training of teacher network at all. You can just remove it. As long as you first train the data using any approximate inference method, like you use for example, use variational inference to train the teacher network. You got the posterior distribution of theta given the data, right?
Yeah.
And then every time inside this for loop, you just sample theta from the posterior distribution, and then plug in the update of WT. That's it.
Yes. So what's the problem with that?
I mean, the problem is they want to use SGLD to train the teacher network. That's why you see the training of the teacher network and the training of student network are mixed together. But if you don't use SGLD to train the teacher network, you can definitely first train the teacher network, as long as you get some posterior distribution about theta.
Oh, okay.
Yeah.
All right. So,
Yeah, nothing else.
oh, okay. So it means that for the SGLD, I think for SGLD, it can be used in the other. I mean, it can be just used to train a Bayesian neural network, right?
Yeah, you can use SGLD to train the Bayesian network. You can use variational inference. You can use stochastic gradient Hamiltonian Monte Carlo sampling.
Oh, okay.
You can use a lot of methods to do that. I mean, SGLD is just one approach.
But why it use the SGLD here instead of other methods to train the Bayesian neural network? Do you have some intuition? Actually, it explained in the paper somewhere. I can show you. So in those two paragraphs they mentioned. So firstly,
Yeah, SGLD perhaps is the simplest stochastic Monte Carlo approach.
oh,
I mean,
okay.
just doing SGD plus Gaussian noise. That's
Okay.
it. And and it is easy to implement. And also the author, you can see Max Bellon, he's the author of HGLD.
Oh, okay.
And you have
Okay,
you have
I
many
see.
other choices. I mean, it's not SGLD is not necessary to be good. I mean, all those stochastic Monte Carlo sampling have a very large bias, although they show that at the limit, the bias will converge to zero, but that is rare in practice.
Okay, I see. Yeah. So, actually, I saw another talk. I think maybe in the New Reps 2020. They present papers related to this one, and they point out some limitation of the SGLD.
It's already 12 and 10. So
Okay.
do you have more things to discuss?
No.
Okay, is this all you have?
Yeah, for today. Actually, I also read some other paper for the quantization, but I didn't prepare slides for them.
Okay, that's fine. Yeah, we can stop now. I think it's time for lunch. Yeah,
Okay.
and why not we just discuss a few more minutes?
Yeah, sure.
Okay, thanks.
So do we have the
Thank you.
afternoon session?
No, we don't have this today.
Okay. And next time is the
It's on Wednesday. Yeah, Wednesday. Longda will present this elliptical slide sampling. Okay. 就你说你看了一下那个什么 workshop 啊，你说2020年有一个talk 是讲什么 SGLD 的缺陷还是什么？
对啊，他就是把这一些文章串起来讲。我可以发给你。
是讲那个 stochastic Monte Carlo sampling 吗？
对啊，但是它包含了那个就其实是这个吧，这个。他这个应该是不是他这是个 workshop 吗？不是一个人讲的。那个我还是分享share一下 screen。就是这个，它其实是讲贝叶斯网络的。
OK。
然后最后一组人讲的就是那个SGLD， 然后其中就包括它的 limitation。
他说 limitation 是什么？
就是其实我没看懂，我可以就是你可以看一下。就是慢吧，慢，然后那个占用内存。
OK。
就其实刚才讲那个Bayesian distillation， 其实有一点忘说了，就是它使用的场景一般就是说是当你用在那种当你的那个 student network， 不是，就是当你的这个任务的 data 尤其是 student 可用的 data 比较少的时候，因为就是这个的话，就是 Bayesian neural network 的优势嘛，就是你当数据少的时候，就是它也可以根据它有一些 prior，所以它还是能够做出一些比较好的 prediction。然后但是对 CNN 来说，它就容易 overfitting。然后呢，还有一个就是说，它可以用在那个active learning，还有那个 reinforcement learning，就是这个上面。
OK， 这里面没有说这个 SGLD 它的这个实际的 performance。
它你是指那个什么样的 performance？是指一些 accuracy，还是指它的 speed？
对，其实我对他们这些人提的这些东西一直都很不爽，原因是因为他们比较都没有好好去认真比较过这个 uncertainty quantification 的问题，他们全是去看一下你的这个 prediction accuracy， 这个有什么用啊？那我拿 SGD 直接拿 SGD 做不就完了？你既然是做这个 Monte Carlo sampling 的话，就是说我们可以做 posterior inference。posterior inference 最重要的是 posterior distribution 的这个东西好与不好。
那你怎么去衡量它好不好？就是通过它的 uncertainty 就能确定吗？
对啊，这里面就有问题。可能一些比较常见的做法是算那个 test log likelihood， 这是一种常见的做法。但是 test log likelihood 其实也没有那么好。还有一种就是跟这个 golden standard 进行对比，比如说你就用 HMC 去 sample， 然后看看 HMC estimate 出来的这个 posterior distribution 的 shape 和你这个近似方法得到的是不是比较接近？我记得当时潘志萌在讲这个 SGHMC 的时候，他们那个文章非常搞笑，他最后居然比较的就是一个 point estimation 它的 accuracy， 这个那你用 SGHMC 干嘛？对，你就用 SGD 就完了。
是啊，就是它确实是，它其实就是想强调 point estimation 不够好嘛，就是所以才用这个。
我们不用 point estimation， 或者是我们想追求更多的，比如说 posterior variance 这些东西。
对。
最根本原因是我们需要知道 uncertain quantification， 但是现在这些做 Bayesian paper 的话，他们都不去比较这个，或者它非常简单。你看 SGLD 那个原始 paper， 他就给你了2个例子，然后去画一下那个图，然后就那是极其简单的例子。那这个一个例子就是说我有一个什么来着？它是一个很简单的一个 nonlinear regression 的问题，然后他拿这个 HMC 和那个什么跑了一下，然后看两个 posterior 的 distribution 的样子比较接近，然后另外一个就是连那什么都没有，就直接用个软路 network 看它那个 prediction 的那个东西，那个其实说明不了什么问题。
OK， 就是你说的就是这个第一篇是吧 ？Bayesian learning。
对他们倒是第一篇那个这是 Max Valley 和 EY 泰做的嘛？啊，这问 dynamics。他那个文章，在 evaluate 的时候，我个人是觉得没有什么，其实没有 evaluate 出来什么东西。
就是你觉得它的 uncertainty 它没有，它其实这是它的 target， 但是它并没有去做 evaluate 是吧？
他 somewhat 做了一点点，但是非常的，你可以对啊，你可以把那个文章打开，你看那个 figure one。
他这文章好早呀，2011。
对，很早的一篇文章呢，你可以往下看 figure one 的。
那感觉 Max Valley 现在还是很那个，他还是挺高产的，就是感觉每年都会出挺多文章的。
他有年要招20个PhD， 你想想。
我一直以为，我不知道为什么，我一直以为他是一个比较，我以为他可能才毕业不久。
不是。
你说表一是吧 ？Table one。
对，在上面，在前面的。哎，你又跑到那什么去了？
对，
应该是 figure five，那不是 figure five，是 page five。 对，你看那个 Figure One，你看它这个是可以真实算出来的 posterior，然后它这个形状跟这个稍微 match 一点，然后他就说这个他抓住，但其实这很难说的，你咋知道这有两个坨呢？两坨这看的不是很明显的。
这个那是不是其他的就是比较接近于那种类似于圆形，这个是扁的？
你可以这么说，但是我更怀疑，你说你把这个 posterior distribution，你把那个 joint probability 调一调，它一定可以弄成两个更明显的圆形嘛，对吧？如果它可以弄成这样一个和这样一个，然后你再用你的东西看你能不能把这个 mode 把这两个 mode 抓住。
OK
啊，但是他没有这么做，弄了一个非常这个扁的，看起来像长条一样的东西。那你就很难说这个。我怀疑是他们试过了，就是你弄成这两个，弄成这样，很明显的他抓不住的。他因为 sample 一样的问题，就是 sample 你一旦跳到一个 mode 里以后，想要跳出来到另外一个 mode 是很难的。虽然理论上你可以跳出来，但实际上很难。就像你用模拟退火也好，或者那种 global optimization，你从那边 jump 出来，花的时间非常长。
OK，
所以这里边它的那个怎么说呢？就是说你的这个 performance，尤其是 uncertain quantification 的 performance 就很难说的。它后面都模拟一些什么 instability，这就 who cares 这东西的。
所以其实是不是说就是 SGLD 它本意它其实是在 training 过程中它是会有不同的这种 posterior 的分布，但事实上你觉得它有可能只是学到一种，就是从始到终这个可能变化不大。
它不是说就是不同，你把它看成是一个 dynamic system 就行，就是所有的 SGD 都是一种 dynamic system。然后按照道理来说，就有理论可以证明的，就是说，当你这个 dynamic system 就是一种系统演化嘛，当你演化到一个静态平衡的station 的状态的时候，这个东西应该和真实的 posterior 是一样的。但这里面关键最难的地方就在于你不知道什么时候到了 stationary 的这个状态。
对，
所以你也不知道你是不是到了这个。
但是这个时候你通过它的 prediction 的就是是否正确和它的 uncertainty 是否正确，这个是不一致的吗？
这当然可能是不一致的。我有一些 prediction 还就是效果相当不错，但是这个东西我的这个 positive variance 还没到。就比如说我已经到了这个点附近了，但是我要继续 sample 的话，我得把这些空间都走遍了，然后我才能知道它这个 posterior shape。我不能说我刚 jump 到这儿我就说我结束了，那不行。
那其实就比如说刚才的那个算法里面，它就是那个 SGD 和SGLD 是同步去跑嘛，他们俩跑相同的 APEC， 所以但是他们有可能他们的就是那个变化程度是不一样的，就像你刚刚说的，可能有一个已经优化的差不多，但另外一个还没有到一个比较好的。
对，没错，但这些问题他都忽略掉。那个其实它那个 Bayesian dark knowledge 非常其实是非常简单的一个 paper。
Okay. 对，它主要就是用了，我觉得其实这个文章对我来说，我觉得挺好的，因为我感觉我读它的 introduction 我就花了很长时间，因为感觉每句就很多话，我就觉得大部分的话我都要去查一下他到底在说什么，就可能是对那个 Bayesian neural network 这一套，就是刚开始就不太理解，所以就是后面的话，我就觉得他这个写的很好吧，就是那个从前到后他到底要做什么，然后每一步他为什么这么选择，就是他都说的很详细，然后最后提出的方法就是用 SGLD，然后再加上一个 distillation 这样来做，就好就可能确实是它的 method 这部分其实应该不是很复杂，就如果理解了的话，应该就问题不大。然后它这里面其实还分了做 classification 和 regression 两个任务，就会有一些区别吧。
啊，这只是那个 technique 上有一点点的区别，这没有什么。
对，就是我觉得感觉还是方法比较简单，就是如果懂了的话，就应该挺简单的。如果就是对那个这个base 网络这些没有那么熟悉的话，它其实是一个很好的入门吧。就是他会把这个东西讲的，就从前到后都给捋一遍。
OK，反正因为基本上是这样的一个背景，但是其实我在想这个问题，就是说，如果你把 student network 和这个 teacher network 是给它 align 起来，然后你的目标是一样的事情，那你再加一个 sparse prime，你不是一样，你可以一样可以做这事儿，不一样是 compression 吗？
其实我觉得这个周末其实我是看了很多文章，就导致我最后目标其实就不是很清晰，我到底要讲哪篇文章？其实就是把 distillation 和 pruning 结合起来，其实也有文章，但我看了一下，我觉得文章感觉质量不是很高吧。然后然后
你说他发
我其实
的地方，他发的地方不好是吧？
对对对，就发一些 workshop，然后我觉得就是看起来就反正至少不会像这一篇一样，就像这一篇我就觉得我可以学到东西，像那个的话就感觉就不是很，至少他介绍他的工作 motivation 不是很强吧，就是然后当然我觉得我可以接着再看一下。目前的话就是同时把贝叶斯和那个 distillation 还有 pruning 结合的文章我还没看到，就主要是把应该是有，但是不是那个好文章。然后主要是我现在在看的是把 distillation 和 pruning 结合起来，还把 distillation 和quantization 结合起来，就是也是呃，但是那一条线我还就是那两条线我还没看完吧。
OK，
就主要是我觉得那个目标不太清晰，看的特别杂，然后有一些就是也没有理解过去，所以就是今天就准备的不充分。
啊，这个没有关系，就我们要了解越多的话，对这个方向就知道的越清楚。你要做哪一个问题的时候，就会突然之间就会觉得做这个问题比较有意义，就你要找一个缝隙，就是刚好做这件事情是很有意义的一件事情。
就现在的话，做 distillation，我觉得他们现在这个常用的方法，就另外有一个用贝叶斯的角度来做 distillation，它那个就是和 transfer learning 相结合。它那篇是我给你看个大概的那个它的那个 figure one，它的就这个，你大概就可以看到，就是它就是一个 input 呢，然后它这里面是用那个是用 mutual information 来比较，就是 student 它的各个层之间的互信息。
OK，
然后呢，但是它这个里面具体的做法，用 mutual information 的具体解法其实是用贝斯这一套东西来解的。他就是想把那个统一，就是说我在那个中间层去看他们之间的相互的关系，和他在最后一层看他们 label，就把这两个要统一在一起。但是这个的话，
那它岂不是让这个 student network 和这个 teacher network 层数是一样吗？
呃应该是的，但是他们可以每一层的宽度不一样。
我看作者列表。
你有认识的人吗？
OK，这边那个 Neil Lawrence 做 GP 那个人，还有这个 Andrews 什么
嗯
Damino，
嗯
还有这个孙苏，这是韩国人。
嗯
OK，这是发的什么？19年的那个 CPR 是吧？
呃，我忘了，反正应该是 CVPR 或者是什么，看这个格式应该是 CVPR 吧。 但是肯定是 CVPR 或者是 SML 之类的文章，这个会有。然后对它这个的话，就是用到的，但是它其实是 knowledge transfer 嘛，也不就是它这个里面就是 teacher 和 student 的 teacher 和 student 就是它的一个可以是 CNN，一个是 MLP。所以你
OK
刚才说他们的深度是一样的，我印象中是看到是这么说的，但我还要确认一下。
OK
然后并且他们的 task 都可以是不一样的，就是
OK
transfer learning 嘛，就比如说一个在大的数据集上，一个在小的数据集上，就是这个的话，嗯，我觉得，但是他现在他这个不管怎么样的话，他现在目前做的其实都还是，比如说像他的 output， 他的 output 的话去看他前面说的 cross entropy， 或者是统一的来说是 KL divergency， 都还是他的 output 来做这个的。然后的话，像然后的话那个像我们之前想的那个可能是在 output 之前的那一层。
对，我们之前就你之前跟我说的那个，其实还是在做 post pruning。
对，但是
我觉得这两个东西的之前的界限也并不明显的。这 student network 感觉更像是从头开始学的，和
对，
那个
这个是一个完
teacher
全新的你任意的一个 architecture 都行。然
嗯
后那个的话其实是它的一个子网络嘛，就是说你在或者是说你在 search 一个子网络的时候，能不能用到 distillation？我目前其实是没有看到，就是说把 pruning 和 distillation 其实有，但是我没有看，但是那是一篇 NLP 的文章。现在的话不是 GPT-3 是特别大嘛，
嗯
是170亿个参数吧，好像。然后我之前那个 Three 不是发给我一篇文章，它其实就是把那个 GPT-3 有一个 teacher network， 有一个 student network，因为 GPT-3 其实就是也是那个 transformer 嘛，就是怎么样去对 transformer 进行 pruning， 它其实也是那个用了一个 distillation 来做的。然后那个的，对，那个的话是我印象中是把 prune， 但那个我不记得是不是 pruning， 那个可能不是 pruning， 也仅仅是 distillation， 因为 pruning 通常都是说子网络嘛，所以目前我其实就是说用子网络和 distillation 结合的，我目前没有看到 exactly 这么做的，我不知道为什么这么做不好。然后因为这个的话，应该可能大家可能都会很容易想到，但是为什么不做？我觉得可能得想一下。但是
哎，
我看到了，
你不是说你看过一些 workshop paper，把
就是
distillation 和那个什么结合的吗？
我可以给你看一下，就是嗯。看一下这一篇是把 distillation 和quantization 结合的，
OK，
然后
是这个 filter distillation for network compression 吗？
这个是一个 workshop 的文章，就是这个是 weight pruning 和 distillation， 然后我主要是看它这个图，我当时就看的有点困惑了。
OK，
这个的话，我可以再细看一下，因为我觉得它写的不是很清楚，觉得感觉不太好。当然，我可以看一下它这个。我本来是想通过这篇文章找一下它的那个 related work， 看有没有就之前别人就这么做的。对，但是我觉得它 related work 写的也不太好，就是写的非常泛吧。像 knowledge distillation 就是 就是谈泛泛的 knowledge distillation，就 weight pruning 就是 weight pruning，然后把它们两个结合的话，我感觉好像没有说的特别清楚。那这个我再看一遍，那我把这篇再看一下，这个就是我看到的做 distillation 和 pruning 相结合的。然后英特尔的那一篇文章，我应该也可以再找来看一下，它有没有用到 pruning，还是说只是用 distillation 来做 compression。然后的话，另外的就是之前看到的那个，就这一篇。这一篇的话，就是把那个 distillation 和 quantization 结合。quantization 的方法其实比我之前想象的要有技巧一点吧。就是所以就这个这篇我还没有看完。
OK，
但是如果想做 quantization 的话，其实我不知道会不会有一些硬件上的要求，就是因为就是你的 quantization 它主要是比如说quantization 就是那样的，就是你去规定你的就是它就是用这种方法，就是它就是用这样的一个这种方法，就是说你去看一下你的目标的是要用多大，比如说是4个 byte， 或者是现在就大家通常用是 float 32嘛，就是4个 byte， 你有可能只需要用到2个 bit 或者4个 bit 这种，或者8个 bit 就1个 byte。那你要达到这种的话，它可能它会有一些技巧来做那个quantization，然后你做了那个 quantization 之后的话，还有一些怎么复原它的精度，怎么让它的精度尽量能还原，它会有很多技巧在。然后这个的话可能会得看一些前面的文章。然后这儿 distillation 我还没看明白它是怎么和 distillation 结合的。我看这个主要是想看一下它是怎么结合的吧。我觉得这个的话，它的结合的方式应该不管是用 quantization 还是 distillation 应该都是一致的。
OK，可以，你可以继续看。
可以后面再跟你讨论一下。
对，继续看以后，然后我们看一看，应该就可以找到一个问题，就可以就值得做的问题，就可以开始进去了。
可以。
行，你那个 committee form 了没有？你是不是现在 committee 还没弄呢？
还没有，就是我跟 Siri 确认一下，它应该属于是校外的。然后校内的话，对，我准备去发邮件问一下，应该如果是Torga 应该是属于校内的吧？它属于外系还是 CS 的？这个我可能要确认一下。
我觉得有可能是外系的。
那我除了 Vivek， 我还要再找一个人，你有推荐的吗？
你们是不想找 Tucker 是吧？你是不想找 Tucker？
我也可以找。我觉得 Tucker 的话，他就是我之前做过他 TA，然后他就是跟他学生吐槽过我和另外一个 TA， 我就怕他到时候就是感觉就是会有什么意见。但是 Three 就是说他曾经帮他的学生做过 committee， 而且是有2个学生吧，所以他觉得 Tucker 应该会答应的。
对啊，我还是 Tucker 另外一个学生的 committee。对，他第一个学生就那个 committee，我在里头。我以为你害怕 Tucker 比较picky 还是什么。
Tucker 他应该，我觉得他对这些不太懂吧。我其实不担心他那个什么。
他是为什么吐槽你？你没好好给他干还是什么？
就是他就是给他做贴的时候，就是题目，相当于题目他其实是 follow 那个Georgia Tech 的那个 Siri 的课，然后呢， 他们的那个课就是有一些题目，但是我们有的时候用他们的题目，有的时候要求我们自己出题目，就出完题目我们还要自己做，就是自己做。然后他吐槽我是因为，我那次做也是春季嘛，春季的话3月份是 ECCV 嘛。ECCV 我就跟他说我当时要赶一个文章，我说那个批的作业我能不能等春假之后再批，然后他就很不高兴，然后就跟他的学生说就吐槽我，然后就这样。
我觉得这个有没有这不是什么大不了的事情。
好 ，OK。
这个
我其实
不是什么大不了
我可以那个写件，我可以找他。那就是因为上次你说是要，就是我找 committee 的时候是要先把 proposal 写好，还是可以只用列
可以
一下？
先问他们愿不愿意做你的 committee， 确定好之后，然后你再写 proposal。
好。但是
就是
我应该
写好之后，
需要
可以 schedule 那个schedule 那个 qualifier。
好，我应该需要就是简单介绍一下我做的工作吧。
对，那肯定啊，你肯定得花2-3句话，大概介绍你做的是什么。
行。那除了 Tucker 之外，有备选的吗？
备选熟人的话，麦科比呗，但麦科比他不是做 CV 的，他完全不懂你的东西。
我感觉我现在也没有做 CV。
What else？你要更加实际一点啊，艾青瑶。
那青瑶，
艾青瑶可能更加实践一点，或者艾
我都还没
青瑶吧，或者你要是觉得觉得那啥的，他毕竟他还是做检索那些东西的话，他是比较应用一点。还有谁？张牧的话是做那个 security 的 ，security 这个有点太远了。
我可以先从 Tucker 写邮件吧，我觉得反正
或者
就是
Ross， 你如果想找 Ross Whitaker 也行，但我不知道 Ross 他
不知道吧？对，你说的 Ross 的话，
系主任之前系主任的。
对他不是那个是 Sedan 的那个现在的那个 advisor 嘛，然后 Sedan 的就觉得经常应该是可能是联系不到他吧，他好像快退休了吧，或者是处于退休状态。
你说 Ross 学生现在联系不到 Ross。
反正 Sedan 的是联系不到，不知道他的别的学生能不能联系到，也不是联系不到吧，就是不怎么管事儿。
他是不是手下还有学生叫陶文正？
对啊。
陶文正在那做的怎么样？
我感觉他文章也不是很多吧，然后陶文正因为疫情，他基本上很少出门，所以跟他交流不多。
那行啊，我觉得你可以先试下Tucker，可能跟你的这个背景，或者那个 Alan Counts，他是新来的 faculty，就是也是做 robotics 的。你要是觉得 Tucker 对你有意见的话，那我觉得 Tucker 也没有必要为这个事儿对你有意见。
对他，我觉得他就其实没什么。其实，其实我是稍微是因为有一件事情，当时我有点生气吧，但是其实后来想想跟 Tucker 也没有关系，就是 Three 他去年9月份不是说不回来了吗？但这个事情没有任何人告诉我。然后中间发生一件事情是8月份的时候 ，Tucker 直接跟他的学生说，我们这个 lab 已经 close 了，说找我们要借一个那个摄像，借一个借一个那种双目的那个摄像机 camera，然后说最好能够不还给我们。他就说的特别露骨，对他学生说你就让他的学生就是要从我这儿借一个 camera，并且最好是能够长期 keep 它。 我当时就有点生气，我觉得，我觉得这个你这个事情，就是觉得这个事情你不能跟我说呀，就是你要找老师嘛，你要跟我说，我没办法决定。而且他说，但是其实我当时生气是因为我完全不知道 Three 当时不回来了，我就觉得他这么说就感觉很不
意思你是说
尊重人。
他找你，你直接说的？
他跟他的学生直接这么说的，他学生直接截图给我了，就是原话就是说我就是那个 Three 这个 lab 已经 closed 了，然后呢就是你最好把那个camera 就能够永久的保留，就不用还给他们。我就觉得这个就让我感觉不太舒服，但我后面想一下，我生气点是因为我当时其实并不知道 Three 他不回学校了，但所以我其实后面也没什么，所以当
这个和
时
你没有什么关系，这个你没有必要为这件事操心。
对，所以我觉得我可能生气点也不是生气在那个 Tucker 那个上面，所以其实我现在没有什么，就是当时我就不太想找他，但现在我觉得可能这也没什么。那我就先给Tucker 和那个 Wilk 发邮件吧，然后看他们的反应。
那个谁，Three 他到底是什么 plan？他是要再回学术界，还是在google 一直待着？
我不知道，我问过他，但是他说
不确定。
对他不确定，他应该是想回学术界吧。就是现在主要是他家里人那个学位还没读完吧，就我也搞不清楚，他好像又加了时间，所以最后可能是看一起找工作找到哪儿吧，我猜就是。
I see。那行吧，那你这个在可预期的时间，你还是赶紧把你的毕业事情搞完吧。
嗯，行，那我这两天我给那个 Wilk 和 Tucker 先写个邮件。
对，你先把这个 committee 组好，committee 组好以后，你花一个这个，当然你论文继续读吧，花个一周时间，给自己定一个这个期限，就是一周时间，把这个 proposal 写了以后发给他们，然后 request 的那个问题，给他们大概至少得2周，甚至可能得三周的时间让他们出问题，这样你很快把 written qualifier 给它过掉。
嗯，可以，可以。
那行，那先这样。